Hello everybody, welcome back to the radar systems class. I am Dr. Muhammad Hayat Razvi. Now the topic is simple form of radar equation. In this topic, we are going to derive a simple form of radar equation to find the maximum range of radar in terms of total power transmitted and aperture area of the antenna and gain and all other things. Now consider if the total power transmitted by a radar antenna with the range R is Pt divided by 4 pi r square. Almost every antenna lobe is spherical in nature. So if an antenna with a total power of Pt is transmitting a power, the power density of isotropic antenna is normally, see, when you want to measure the density, you need to divide it by the area. Example, population density. If total number of population in a village divided by the village area gives you the population density of the village. Similarly, if you want to know the population power density of an isotropic antenna, you need to divide the total power of the antenna with the area. Normally, the spherical in nature antenna lobe will be in spherical in nature, so the power density will be Pt by 4 pi r square. If the antenna is isotropic, this will be the power density, which don't have any directivity. Normally, in all the practical cases, the antennas are directive. Particularly, the radar antennas that we are using with the radar systems are directive in nature. So, all the directive antennas will have a particular gain. The antenna with a gain G dissipates a power with a power density of Ptg by 4 pi r square, where G is the gain of the antenna. Now the power density of directive antenna is Ptg by 4 pi r square. Now consider this power density is transmitted by the antenna. The amount of incident power intercepted by the target and radiated back is called the echo. Now the power density of echo signal at radar is, along with Ptg by 4 pi r square, you should consider the radar cross section sigma divided by 4 pi r square. See, this is echo power. Echo power is measured in terms of the aperture area of the target, which is nothing but the cross section of the target. If the cross section of the target is very large, then the received echo power amount will be large. If it is very little target, its cross section will be little and hence less power. So echo power always is in terms of cross section of the target. So here the power density of the echo signal at radar is Ptg by 4 pi r square into sigma by 4 pi r square. Now the echo signal has come to the radar receiver. Now it is the size of the antenna which can capture the received power. Basically, the echo is very little in quantity. A little quantity echo signal, when received at the antenna with a smaller antenna, consider antenna size is very little. Now the received power will be very minute or negligible. If you have a large antenna, that gives a very large big difference in the amount of received power. So the aperture of the receiving antenna is also a parameter to measure the received power. Understood? Now, if the effective area of the receiving antenna is AE and the received power is denoted by PR, then received power PR, as written in this equation, PR is equal to PTG by 4 pi r square and sigma by 4 pi r square into the aperture area of the receiving antenna, which is AE. Now, this can be simplified as PTGAE sigma by 4 pi square r power 4, where r is the radar range. Now, let us write the equation for radar range in terms of minimum detectable signal. See, this minimum detectable signal concept is, if you have a radar antenna with a range, for example, if you have a radar antenna with a range of 1 kilometer, now consider what is the highest distance that your radar can measure is 1 kilometer. The echo signal which hits the target at a distance of 1 kilometer and comes back will obviously can be treated as the least power that your antenna can receive, irrespective of the cross section of the target. If your radar signal is going to its highest distance and coming back, then it is treated as the minimum detectable signal. Now, PR, received power, in the case of maximum distance, is denoted by S min. That is what is written in the spine. It occurs when the received echo signal power PR just equals to minimum detectable signal at a distance R max. Therefore, in the previous case, we wrote R. Now we are writing it as R max. Now R max is PTGAE by 4 pi r square S min, because here it was PR and here it was R. Now it has become R max. This PR has to come here. In the place of PR, we are writing S min, because R power 4 was there. Now that R power 4 has become whole power 1 by 4. So PTGAE sigma by 4 pi square S min whole power 1 by 4. Now let us rewrite this equation in terms of replace this G with aperture of the antenna and lambda square. G is equal to 4 pi AE by lambda square, where lambda is the wavelength of the transmitted signal and AE is the antenna aperture. Replacing that, what will you get? Here you will get 4 pi AE in place of G. This 4 pi will cancels with this 4 pi, and AE again with AE multiplied will give you AE square. Now this equation has become PT AE square sigma by 4 pi lambda square S min whole power 1 by 4. Hope I understood this topic. If you have any doubts, write your doubts in the comment boxes. The next topic is radar block diagram and operation. As we have seen in the previous video, the radar antenna with simply one transmitter and one receiver box is connected to the antenna. That was the basic principle of radar. Now, practically, the radar block diagram constitutes an antenna connected to a duplexer. Here, role of the duplexer is to isolate transmitter and receiver with the antenna. As we have seen, radar first transmits a pulse, then starts waiting for the echo to come. When echo has come, it will, depending upon this is the basic block. When echo has come, it will measure the time taken by the electromagnetic pulse to go to the target and come back. Depending upon this time, we can measure the radar range. Now, the antenna first serves as the transmitting antenna. After transmitting this whole pulse, the antenna's role has now changed to receiving antenna. Now it will for the whole time after the pulse, it will be acting as a receiving antenna. So one antenna is enough for the radar to operate comfortably. Now this antenna, while receiving, if the received amount of power reaches the transmitter, there is a tendency or there is a chance of transmitter to break down. To overcome that problem, what we did, we have inserted a duplexer. The role of the duplexer is when the signal is signal is transmitting from transmitter to the antenna, it will be acting as it will be allowing the signal to go to the antenna. While receiving, it will not allow the signal which is received to again go back to the transmitter, but it will direct the received signal to the receiver section. That is the role of duplexer. Duplexer protects the transmitter as well as receiver because the transmitter pumps kilowatts of power into the antenna. If that kilowatts of power is being fed to this low noise amplifier, there is a tendency that this amplifier burns out. So that is a problem that will not be allowed. These two are isolated during transmission cycle. During the receiving cycle, again transmitter and receiver are isolated from each other. So after receiving the signal, the first stage will definitely have noise along with the actual signal. To remove the noise and to amplify the weak signal which is received, we definitely need one low noise amplifier, that is this low noise RF amplifier. As you can imagine, radar always uses microwave frequencies which are of the order of gigahertz. No amplifier works well at higher frequencies because of shock noise, thermal noise, all kinds of noises will influence the degradation of the system performance. To overcome that problem, we need to convert it to a lower frequency, which is called as intermediate frequency. How can we do that? With the help of a mixer and a local oscillator, you can convert any frequency into any other required frequency, which is called as IF frequency. Now the received signal is fed to a mixer. Consider if the received signal is 10 gigahertz. Now this local oscillator is maintained at 9.8 gigahertz. Now the IF amplifier, what the IF amplifier will get? 10 gigahertz minus 9.8 gigahertz is 200 megahertz. Output of the mixer is F1. If this frequency is F1 and this frequency is F2, output of the mixer will be F1 plus or minus F2. F1 plus F2 will have higher frequency which will be neglected or discarded. F1 minus F2 will be a lower quantity which is passed to the IF amplifier and a matched filter. The first section of this IF amplifier will be matched section, which will discard the high frequencies and allow low frequencies, in our example which is 200 megahertz or even lower also depending upon the requirement. So the circuits from now onwards will get this IF frequency which is lower, considerably very lower. Now the system performance will be very fine. After this IF amplifier, there is a detector which is noted as 2D detector. Why 2D detector? One dimension is the amplitude. Depending upon the amplitude of the echo signal, we can estimate the size of the target. If there is an amplitude in the echo, we can feel like there is a target. If the amplitude is very large, we can treat that the target is very large. If the amplitude is very less, we can treat the amplitude is the target size is very little. So it is one dimension is its amplitude. Another dimension is you might have seen uh, antennas rotating over the large ships and near the airports also. The air traffic control radar antennas will always be revolving. These antennas are rotated 360 degrees so that the transmitted power transmits in all the 360 degrees, all the directions, and the information about all the directions should be there with the radar section, so that we can identify from which direction the vehicles are coming and to which direction the vehicles are going. So one dimension of this 2D detector is one is direction, another one is amplitude. That is why it is called as 2D detector. The 2D detector is followed by a video amplifier. Detector is nothing but demodulator. The radar signal is pulse amplitude modulated. Pulse amplitude modulated, PAM. Now this PAM signal is demodulated at the detector. The demodulated signal will be having only envelope. That envelope will be very weak. It will be amplified to a proper level and given to a display which is called as a scope. Now on the a scope you will find a very weak signal along with some peaks. Wherever there is a peak, you can consider that as the echo signal, and depending upon the time of echo signal and its amplitude, you can estimate the distance or the range of the target along with the size of the target. Here the role of pulse modulator, the name itself is indicating it will be a modulator which is modulating a high frequency carrier of some gigahertz frequency with a narrow pulse. Now that modulated narrow pulse of carrier waves will be fed to the transmitter, which is normally a power amplifier. After amplifying, it is given to a duplexer, then to the antenna, which will be transmitting, and the receiver, as we have seen, is finally given to the display, which is also called as a scope or simply the amplitude scope. Hope I understood. Hope all of you might have understood this topic. If there is any doubt, please leave your comments in the comment boxes. I'll definitely try to answer. Thank you.